First of all, thanks to all the organizers for setting up this wonderful conference. And thanks for the effort, really, and for giving me the opportunity to be here presenting my work. I'm Clemente. I'm a PhD student at SISSA here in Trieste. And today I will talk about, let's say, about trying to challenge the ultralight dark matter paradigm with pulsar timing arrays. Admittedly, this is a bit a catchy title, but what I hope to do here is to convince you that pulsar timing arrays can be useful instrument not only to test the stochastic gravitational wave background as it has been done recently, but also to try to investigate the nature of dark matter. So the outline of the talk will be the following one. Firstly, I will talk a little bit, spend a few words on pulsar timing arrays, basically trying to convey what pulsar timing arrays are and what do they do. I will spend a few words on the timing model and in particular, how to look for a signal in pulsar timing arrays. This will be a very fast section. Secondly, I will try to give a little bit of details about ultralight dark matter, a brief introduction and motivation. But also this will be a very fast section because I want to focus my talk to the third part, which is how is it possible to give constraints with pulsar timing arrays on ultralight dark matter. And in particular, I will focus on the gravitationally coupled ultralight dark matter case. This is the most robust scenario, let's say, because if we know one thing about dark matter is that it interacts somehow gravitationally. So I will focus specifically on this scenario here. So let's start with the first part. Pulsar timing arrays are basically collections of pulsars which are used to search for special signatures in their past time of arrival. Basically, they analyze, they are composed of millisecond pulsars, which are very stable clocks. And millisecond pulsars send us very precise signals with a very precise period. So basically, by looking at these periods and at the variation of these periods in time, you can do a lot of things. First of all, you can characterize the noise of the pulsars because we need to understand what pulsars do in order to claim something about dark matter or stochastic gravitational wave background. But then you can test the stochastic gravitational wave background. You can put constraints on primordial black holes, on model of inflation. But here I will discuss how PTAs can give us some information about ultralight dark matter. The challenge in pulsar timing arrays is to relate the observed timing of arrivals, so the time of arrival at the observatory, to the time of emission at the pulsar. And the common way to do that is to divide the travel time, let's say, of the pulse in some steps. First of all, as you can see from the relation, what usually is done is to relate the time of arrival at the observatory to the time of arrival at the solar system barycenter. Then you relate it to the time of arrival at the binary barycenter if you are considering a binary pulsar. And then from there, you relate it to the time of emission at the pulsar. So basically, you're trying to trace the path that this light beam is traveling from the pulsar to the observatory. And just so that you can see how it can be difficult, just to relate the time of arrival at the observatory to the time of arrival at the solar system barycenter, you need to account for lots of terms. You have atmospheric delays, Romer delays, parallax delays, and a lot of other delays, which I don't want to delve into, but I just want you to understand that it is really a challenge to relate the time of arrival at the observatory to the time of emission at the pulsar. So assuming you can do this relation, you can relate these times, you have a recipe. You take the observed time of arrivals, then you fit them accounting for the effect described before, which are parallax delay, Einstein delay, etc., etc. And then you say, okay, I'm fine. I have my full-fledged timing model, and my best fit parameters, it's finished. Unfortunately, or fortunately, depends on the point of view, things are not so easy. Because in fact, in Pulsar timing arrays experiments, the main observable is not the time the time of arrival of the pulse, but it's the timing residual, which is basically the discrepancy between the time of arrival of a pulse with respect to the one you would predict according to the timing model. So basically, you have a set of observation, you fit them, you have a timing model, then you predict that the following pulse is arriving at a specific time. Then you observe the following pulse, and maybe you notice that there is some discrepancy. And you can do this for every time of arrival. And the discrepancy between the observed time of arrivals and the predicted ones, it's called the timing residuals, and it's the main observable in the experiment. This discrepancy can be accounted for some effects. For example, you can say, okay, maybe you just need to fit a little bit better things. You just need to modify a little bit the parameters of the timing model, which is the first here. No, I did something. I think a lot. So here's, okay, this is the point. So I was saying, you can account for these timing residuals by different terms. You can say, okay, maybe you just need to fit a little bit better things. You just need to modify a little bit the parameters. And this is like this first piece here. You can say also, well, you have a measurement, there's some white noise involved into it. That's the second piece. Then can be some red noise, that's the third piece. But then there can also be something else. And it is this something else that we are trying to look into. So once we have modeled possible deviations from the best fit parameters, white noise or red noise, still we have something that we can look, and that hopefully will give us some info about dark matter, stochastic gravitational wave background, etc., etc. So the main message that I want to convey is that in order to look for a signal in pulsar timing arrays, we should model how it affects the timing residuals. So let me come to the second part. I will be very fast on this. Basically, the cold dark matter paradigm has some well-known issues. For example, the CASP problem, the missing satellite problem, and lower than expected central density. They basically all have to deal with the fact that when you look at the inner parts of galaxy, with cold dark matter, you would expect a CASP profile, while what you see is a core profile instead. And so basically, these problems might be alleviated invoking baryonic physics. For example, you can say there's some gravitational steering by supernovae. But still, when you analyze dwarf spheroidal galaxies which have no baryonic activity in the center, it's a bit more cumbersome, let's say. So let's say we need to invoke another mechanism, which is ultralight dark matter in our case. And we focus on a scalar field which has a mass of, let's say, 10 to the minus 22 electron volt, this order of magnitude, 10 to the minus 23, whose de Broglie wavelength acts as a quantum pressure that suppresses power on very small scales. So basically, you are trying to pack ultralight dark matter very in the inner part of the galaxy, but since it behaves as a wave, it tends to spread. So actually, instead of having a CASP profile, in the end, what you end up is a core profile. And the de Broglie wavelength is given by this formula. And you can easily see that the lighter the ultralight dark matter, the bigger the de Broglie wavelength. Okay, I want just to say that this behavior can be seen by solving the relevant set of equations, which is called the Schrodinger-Poisson system. And you can solve that numerically and obtain the profile of ultralight dark matter. But okay, let me come to the third part, which is how can we give constraints on ultralight dark matter from pulsar timing arrays? In the following, we will think of ultralight dark matter as a free scalar field, because we just want to analyze gravitational interactions. And due to the huge occupation number, we can model the scalar field as classical waves. And from the energy momentum tensor, we can, relating to the density of dark matter, we can get a little bit the expression of A in terms as a function of the dark matter density. But then, as we will see, in order to characterize fully the field, we want we want to understand the relation between A and M. And to find the gravitational field produced by ultralight dark matter, we can analyze how it modifies the gravitational, the line element. So basically, what we want to do is to see what effect this ultralight dark matter has close to the pulsar. So if the ultralight dark matter is there, maybe we expect that it will oscillate, and so the pulses will travel in a background which is a little bit oscillating, and so they will arrive a little bit displaced with respect to what we would expect. So basically, let's try to see what happens. We can write the ds square in terms of the gravitational potentials phi and psi. We can split the potential in time-independent and time-dependent parts. And from the trace of the Einstein equations, we can get the formula that you can see at the bottom of the page. Basically, what I want you to focus on is the second part, the second of these three formulae. The first one is not very important because this is a time-independent shift which will be absorbed in the timing model. So we just want to focus on terms which are depending on time. The second part is basically the effect of ultralight dark matter. And as you can see, ultralight dark matter modifies the ds square, giving rise to a potential which relates the density of dark matter with the mass of dark matter. Sorry, which relates the amplitude of the potential, which is psi c, to the mass of the dark matter. So we have a kind of relation. The lighter the dark matter, the higher the effect, the bigger the effect it will give. Now remember what we wrote before. In order to look for a signal in pulsar timing arrays, we have to model how it affects the timing residual. So now we understood how it modifies the line element. Now we want to go from that to the timing, to how we want to understand how it affects the timing residual, which is the discrepancy that we will see in the signal. And skipping a little bit of details, the final formula is the one you can see on the bottom. It basically depends on the amplitude of the potential, which is psi c, on the mass of the dark matter, which is written as 2 pi f, and on the phases of this scalar field at the Earth and at the pulsar. And if you account for some stochasticity in the axion field, basically you have to modify a little bit the formula with a coefficient here, with this phi coefficient here. Okay, so basically, on scales smaller than the Broglie wavelength, the ultralight dark matter scalar field will oscillate coherently with the same phi square. So basically, you have two cases here. So you have the correlated limit in which your de Broglie wavelength is larger than the interpulsar separation, and that means that, and also than the average pulsar Earth separation. So that means that the phi square in the Earth is the same one as the phi square at the pulsar. Or you have the uncorrelated limit, which is basically telling you that the Broglie wavelength is smaller than the interpulsar separation. So these two coefficients will be different at the Earth and at the pulsar. But I told you that the Broglie wavelength depends on the mass. So basically, according to the mass of the candidate, you can have that the candidate, the mass is in the correlated limit or in the uncorrelated limit. So let me come to the results. You can say, okay, we have recently observed an excess with pulsar timing arrays. We want to wonder whether this excess that we observed can be attributed to ultralight dark matter and can be explained with the ultralight dark matter paradigm. So we just want to model the noise of the pulsar, add some white noise, add some red noise, and then we want to say, okay, then there is just dark matter. What do we find? Well, if we just consider dark matter, we find a huge spike, a huge excess for a mass of dark matter, which is 10 to the minus, almost 10 to the minus 23 electron volts. But this is a bit, we should be a bit more careful in this, because ultra-red dark matter, as we wrote it, gives monopolar and not quadrupolar correlation, which instead have been observed. So maybe we should assume, and what we did was assuming that the signal observed in pulsar timing arrays comes from something else, which might be black holes or whatever, comes from something else. And on top of that, so assuming that that signal comes from something else, we want to see if there is some other residual that might be given, might be accounted to dark matter, to ultra-light dark matter. So basically, we perform the analysis in this setting, and what we find is the following result. I will guide a little bit you through the plot. So basically, the violet dashed line is the strain, the potential psi c that corresponds to 100% of ultra-light dark matter. So if there was 100% of ultra-light dark matter, the dashed line would be the effect that we would see in pulsar timing arrays. But actually, we performed the search with the EPTA dataset, and what we found is that instead we are able to constrain the strain below the predicted abundance for 100% of ultra-light dark matter. What does this mean? From the right plot, like looking at the right plot, what we can see is that we are able to constrain the abundance of ultra-light dark matter below the observed dark matter abundance. So basically, if ultra-light dark matter of this mass interval were there, it could not constitute the whole dark matter. So we need to account from something else. And this is the main message that that I want to convey. So coming to the conclusions, pulsar timing arrays are wonderful laboratories to test signature, whatever kind of signatures, in signals coming from pulsars. And it is possible to constrain ultralight dark matter density below the predicted abundance. So if ultralight dark matter was there, or ultralight dark matter of those specific masses was there, it could not be the full, it could not be the 100% of dark matter. And then maybe there are also some other prospects. We could also extend the bounds to ultralight dark matter interacting with matter. And in general, we can test whatever other model just by looking at the effect that it gives on the timing residuals. So feel free to ask whatever question. Thanks a lot for the attention.